My name is Dan Svenstrup, and I'm going to talk about machine learning for medical diagnosis, as Matthias said. This is some work that I actually did when I was at DTU, but I'm actually not at DTU anymore. I'm at something called KMD in Denmark, where we are looking at all the data from the citizens in the municipalities, for example. And we're actually also looking at something related to this. We are looking at data in the health sector, where we're trying to, for example, try to predict if a person is in danger of a fall accident, and then we might be able to take some preventive action in order to prevent that. But this is a topic, a little bit different topic. It's about medical diagnosis, and specifically it's for rare diseases. So the outline of what I'm going to talk about is that I'll first try to motivate why we're even interested in looking at a search engine or search engine for rare diseases, or a decision support tool for medical diagnosis for rare diseases. Then I will talk a little bit about how could we actually improve this decision support engine, and I will talk about some performance optimization and something that we call information completion. So why are we even concerned about these rare diseases? It's because we have a rare disease that's defined as a disease that affects only a small percentage of the population. Here in Europe, it's a disease that affects less than 1 in 2,000. So it seems like it's something that happens really rarely. So why should we even care about this? Or why is it such a big problem? The problem is that there are so many of them. So we have about 7,000 rare diseases, and that means that it is estimated that between 6 and 8% of the European population will be affected by one of these diseases during his or her lifetime. So, and to make things even worse, then we have that each medical professional will perhaps only see a given rare disease once or twice during his entire lifetime. So that means that there will typically be long diagnostic delays and also a lot of errors, and that is of course very bad for both the society, because it costs a lot to have a patient that has to go through a lot of different tests, and also it's very bad for a patient that is, for example, not being diagnosed during a 20-year period, for example. So it is a huge societal problem. So we created this search engine that was a specialized search engine that we tried to make work better than, for example, Google, because we are focusing on a specialized domain, so we can introduce all kinds of special auxiliary information like symptom synonyms and disease synonyms and so on. So we created this search engine where you can, where it has this simple search field, and then you get a list of disease proposals, and then you can click on each of these, and then you can get a description of the disease. Yes, and we can try to improve the quality of this as the decision support tool. We can see this list out here as an automatically generated differential diagnosis. That is a list of potential diseases ranked by their probability of according to the symptoms in the search field. And of course, we can make a better differential diagnosis. That is the obvious way of improving the quality of this tool. But we could also go in another way. We could say, well, sometimes, for example, if I search for pain, then I will get perhaps 1,000 results. And in reality, the problem is that we could never, no matter how well our search engine performed, that would not be enough information. And therefore, it's interesting to try to do what a doctor would do. He would ask for more information, and that is also what we're trying to do with this information completion. That is, we try to query the user for more information. I'll come back to each of these separately in the next slides. So how should we measure this performance? It is when we get this query, then the search engine, it returns this automatically generated differential hypothesis diagnosis, and we could use the probability of having the correct diagnosis in this list could be a good performance metric to see how well this search engine performs. And that metric is called recall at k, and that's just an estimate of how frequent is if we have a search query, what is the probability of having the correct diagnosis in this automatically generated differential diagnosis, this that is on the left side here, right? Okay. So I should also say, well, we also have this problem that I think everybody who is applying machine learning in the real world, we have a problem with finding correct good training data and good test data. So we actually, in order to test this performance, we created our own data set consisting of some symptoms and a ground truth diagnosis. This was created partly by a doctor that created these queries, and also we used something from a game called Medical Jeopardy that is Doctor's Dilemma. It's kind of a medical jeopardy. So, and then we could say, well, in that it's we have a query like a list of symptoms, and then we have to guess the ground truth diagnosis. So, but of course, this is quite time-consuming to create such a data set. So we only have about 500 of those. So how did we try to make this search engine smarter by improving the performance or retrieval performance of the? We used first of all we used improved retrieval models. We tried several different types of networks, neural networks, both on character level and on word level, and also we tried to use both sequence models and these backup words models. And also we investigated two methods for combining the trained models in an ensemble. And the last one was how can we actually, because we don't have a lot of training data, so how can we expand the training data? Our training data consisted of, or our baseline training data consisted of 21,000, almost 22,000 articles about 8,300 diseases. So one thing that you can might notice when you see that number is that for every disease we only have one or two, or perhaps for a few we have perhaps 5 or 6 articles on the same disease. And when you want to train a neural model, then you need actually a lot of different samples for the same class, because we treat this as a classification problem, right? So, and the thing that we did was that we don't really have a training set that says, well, you have these symptoms and then you have this diagnosis. So we did something else and hoped that it would actually transfer to real queries. For each of these articles, we took out random snippets and tried to predict what disease is this snippet from. And then we tried to look at the test set and see if it actually translated to the test set also. And luckily it did. And then I'll come back to that in just a moment. But I should also just finalize this corpus expansion. We did the corpus expansion in 2 ways. We first did it through a static expansion where we tried to increase the number of articles by finding a list of medical websites, and then we tried to extract information from those websites using just simple regular expressions. The second method was by a simple algorithm for inclusion of a collection of case studies. But in order to include a case study, then we, in a way, has to know, well, which disease is this case study about? And we can't really see from the title, for example, of this case study, if it's about Graves' disease or about metastatic melanoma. So we did something else. We included, first of all, we tried to figure out, well, how we built a simple classifier that was able to say, well, is this Graves, what potential diseases is this case study about? And then we included one for Graves' disease and one for metastatic melanoma. The fourth way we tried to optimize performance was by using structured data sources, specifically by including synonym information into the models by using this UMLS database, that is a database of relations between medical concepts. So we ended up with this. And I will not talk that much about it because I think there are three important things in this. I think this is just a small fraction of the models that we actually tried. But we see that for the baseline data set, then we don't really get any improvements compared to these are standard frequency-based models, but we don't really get any better results by using deep learning on those because we simply don't have a large enough data set. And we see as soon as we begin to increase the amount of information or the number of articles, then we get a large increase in performance. That is, the amount of data is very, very important in this, and also the use of ensembles turned out to be quite important. And that is perhaps also quite to be expected because there's a large risk of overfitting when you don't really have that many samples of each class. And it's actually a little bit remarkable that using this snippet idea where you take out a snippet from each article and try to predict what class the article is about, then by using that method we actually don't overfit to this training data, even though we only have one or two articles for each disease. And I think that's quite remarkable, actually. We can also try to take a look at one interesting thing, because in this medical domain, there's a lot of specialized words, and it's perhaps quite easy to be able to, to make a mistake when spelling a medical term. And some of the models that we tried was also based on looking at a text as a sequence of characters. And when we do that, then we don't get the same impact of a misspelling, because when you have a word-based model, then if you change a character, then you change the entire information content of the word. But if you have a character-based model that is just a sequence of words or of characters, then you can interpolate if you have a mistake in your spelling. So this is what this graph shows, that the relative performance actually is twice as good if you have a spelling probability of 20% for each character or misspelling probability of 20% in each character location. Another thing that we noticed was that we couldn't really figure out, well, why don't we get a larger performance increase from these synonyms? Because we don't really get that much of an improvement by using that. And I think part of the explanation can be found if you look at the topmost plot here, because here we have, I think it's a little bit difficult to read here, but we have tumors, tumor, neoplasm, neoplasm, tumor, neoplasm, tumors. That's different ways of saying the same thing, and they actually get the same representation in this word space, because we're using word vectors as input, and if you take a look at those word vectors and project them down to this lower dimensional space, then they will actually fall almost in the same position, meaning that they will be treated equally by the model. So the next part that I'm going to talk about is then this information completion, because in order for a search engine to retrieve the most relevant documents based on a query, it needs the query to be sufficiently informative. That's quite clear. If you give it pain, then it could be a lot of diseases. And that means that in this case, some information seems to be missing from the query in order for the search engine to be able to retrieve relevant content. And of course, if we had been in a clinical setting, then you would ask the patient again to give more information. And this is sort of the purpose of information completion. Try to figure out what kind of data might be missing from the query. So this additional information, that could be, for example, additional test results, other diseases that the user might have, or additional symptoms or some medication. We might have one of the symptoms might actually just be a byproduct of some kind of medication. So now we come back to the problem that was also mentioned in the talk before, that we actually don't have training data readily available. We would like in order to train this, we would like some kind of query, missing information tuples, such that we could try to give the query and then try to predict the missing information. But unfortunately, we don't have that. So we do the same thing as we did for the when we tried to improve the performance. We take a training set sample that is just a snippet of an article, and then we remove one of the words, one of the symptoms or test results or something like that. And then we feed this into our neural network and try to predict what symptom has I deleted. So the problem with this is that these snippets really don't have anything to do with real queries that are often just a list of words. And so we need some way to be able to translate this to something that looks like a query, a standard query. And a standard query that would typically just be a list of symptoms, for example. So we train our models, and then we actually hope that this will translate well to a normal standard query. So let's, these are standard queries. This is almost just a list of symptoms. And these are from our test set that we created in collaboration with a medical professional, and these are actually from this medical jeopardy data set that I talked about. And we see that we have a diagnosis, and then we remove a symptom from this test set sample, and then we give some proposals for what might be missing from the query. And if we take a look at the results, then we can see that if we have tried some different kinds of models, but if we can see here, this is n. That is how many proposals are we giving back to the user, or patient, or doctor. And we can see that if we have 5, then we will get a recall at 5 of about 24% or something like that. That means that if I am presented with a query and I have deleted a symptom, then I will have a probability of 24%, and 1 in 4 proposals, list of proposals would result in a correct symptom. And it should be noted that this is just a lower bound, of course, because if I take if I withhold a symptom like high fever from the query here, high fever, runny nose, sore throat, muscle pains, headache, coughing, and feeling tired, we get these proposals. So actually, it doesn't really. These are actually good proposals, considering that this is a query for influenza. So in that case, we would say, well, the information completion system actually doesn't do what it's supposed to do, but it does in a way anyway, but we cannot really measure this that we actually find something that is relevant, a better performance metric would not be recall at n, it would perhaps be relevancy at n. But the point is that this is just a very low bound of the performance of the system. And we actually implemented this in what should be a pre-consultation app, where we could try to diagnose in an interactive way, where we first had a user that queried the system for, said to the system, well, I'm suffering from a headache and pain in my shoulder, for example. And then we would query the user for additional information that might be relevant for the diagnosis. And this is something that, for example, it could be used when you call to the medical central, and then you, instead of just sitting there waiting in line, then you could be say to this chatbot that, well, I'm suffering from these symptoms, and then you could get additional questions to the patient before he was triaged. But there's a lot of things here that we actually have not discussed in this, and that is, for example, that we could try to include more data using semi-supervised methods and some active learning. And I also think that if we looked at the results, then we saw that the thing that actually improved performance the most was inclusion of more training data. So this is actually a direction that we will be looking at in the future also. Also, the use of prevalence data is extremely important because it can completely alter. If you know the prevalence of a disease and it's very rare, then you might have a very good fit for your symptoms to your diagnosis, but that doesn't really matter if it matters, but if you have a very low prevalence for the disease, then the probability of the disease is very much lowered. So, but unfortunately, we haven't really been able to obtain any reliable prevalence data from anywhere, because if you look at, for example, hospital admissions, that would give a low prevalence to, for example, influenza, and that's not really what we're looking for. We're looking for prevalence data for the general practitioners in this case. So, also, I think we should also be looking at improved methods for information completion, because the method that I showed actually just do one thing. It tries to predict what might be missing from this query, and it does not take into account what is the diagnostic usefulness of the proposal. So that is also something that could be looked at. For example, we could try to find the piece of information that we would need in order to minimize some cross-entropy error or something like that. So yeah, I think that's it.
So any questions? One here, yes.
So thank you. The last part I didn't get with including prevalence data, because if you do that, your scores will go up. But aren't you then missing part of the point of actually diagnosing rare diseases? If you have an extremely rare disease, it's no point of diagnosing it at all, in that sense. So can you comment a bit on that?
Yeah, actually, I think that there's also, if you want to, for example, use this as a, for example, for the public, then it might be very dangerous not to include the prevalence information, because I think that is actually what is going on when you search, when you use Google for diagnosis. Then you are certainly terminal ill from cancer, for example. So, but of course, in a clinical setting, that would not. Then you really want to know what actually fits to this this specific query, and then you might have a medical professional that can evaluate if this is actually relevant or not.
So I was wondering if you have some symptoms and they could be explained by two different diseases. Either they could be one terrible disease, or they could be vitamin deficiency and pollen allergy.
Yeah.
Does this have some way of giving a suggestion that this might be two different things coupled together?
No, it does not. Not except that you might have that in that case that the probability of each of these diseases might be the same, and you will get them in roughly the same part of the differential diagnosis. So, but of course, that could also be important that if you think that it might be this disease, then you should also look at this other disease. So this is also something that we had been thinking about doing, that you could find some similar cases. For example, if you have this disease, then this is very similar to that disease.
I suppose my question is in a sense related.
Yeah.
If you're interested particularly in helping with the diagnosis of rare diseases, but your training data presumably has a lot more information about common diseases. How do you avoid that sort of mass of data swamping the
rare disease search?
Yeah, exactly.
Well, it should also be like it's kind of a hybrid between actually rare disease. It started as a completely clean rare disease engine, and then it has turned into something that is more like it also includes things like influenza and stuff like that. But it shouldn't really. Rare disease is treated in the same way as a more common disease. It's not like the thing that you should think about is, I think, the number of articles on each of the diseases. And I think the training set includes more articles about the rare diseases than the common diseases.
So in that sense, your training, compared to the real-world prevalence, your training is very highly biased towards the rare diseases.
So,
yeah.
It wasn't clear to me, but in PubMed you have all these mesh terms, so they actually classify the papers for you quite neatly.
Yeah.
How much of that do you use?
Well, we don't really use. We use it for in order to classify our articles in our training set. But you're talking about the inclusion of PubMed case studies that I talked about, right?
No, I was thinking about for the mesh terms that you have for all the PubMed articles, so that they are classified by PubMed when they are entered into the database.
Yeah, but what is that a classification of what disease it's at, or
the content of the paper?
Okay, the content of the paper, but that can be quite ambiguous, right?
Yeah,
is it always about one disease?
I think my guess would that it would help. It would be even more accurate than machine learning tools for that, because it's hand generated.
Yeah, that's true. That's true. But we were not really able to find that information in the PubMed articles. So, but yeah.
But you get it when you do searches from PubMed.
Yeah, but we downloaded this open source or open access dataset, and I don't think that we couldn't really find in that dataset. There's no thing like that. So, but perhaps it is possible to take the title, search on PubMed, and then get it in that way. I would not say that that's impossible. That would be a better idea. If we can definitely say this is an article about Graves' disease, then that would be, of course, better. So,
because I think that they actually read all the papers and classify them.
Okay, yeah. So that would be a good idea.
Okay, let's thank Don again.